Okay, here is the mark scheme for the Year 9 2013 paper. I'll try and do this cold so that I can see whether the eye would trip up and what to focus on. Okay, so here we go. Question 1. Rachel and Finn are pushing a loaded shopping trolley. Calculate the total force present. Well, if you notice, there are two forces acting. Two forces acting in the same direction, so therefore the resultant force is the addition of the two forces. Straightforward. And what is the total force otherwise known as? Well, it's the resultant force, and that's something which you just need to know. Definitely not the mean force and the answer force. That's a terrible suggestion. So it's the resultant force. Now, it's moving at a constant speed, and hopefully we can remember to ourselves that at a constant speed, the resultant force must equal 0. So therefore, if there is 50 newtons acting in that direction, there must be 50 newtons acting backwards. So add an arrow to represent the force in the diagram. Well, the friction comes from the wheels of 50 newtons. Sorry, that looks like 80. It should be 50. And where does that one come from? Well, it comes from friction. Okay, probably one for the value and one for the naming it. So add arrows to represent the forces acting in the trolley in the vertical direction. Well, we know definitely that weight is acting. And remember, with a free body diagram, we need to not only draw the length of the arrow, label it correctly, but also show that it's coming from the centre of mass. So, yes, good. And then we have, from the wheels, upthrust. Contact point. So you must start them where there is a contact with the ground. And also the addition of those two should be the same as the weight, because it's not moving vertically. Its resultant force vertically must be 0. Explain why you've drawn them. Well, pretty much we'll explain again. The weight is acting downwards from the centre of mass. The upthrust from the wheels, and they must be even in length. Good. Probably too much detail there, but nonetheless that's not a bad thing. Okay, electromagnetic spectrum question. Simply asking you to identify which is which identifies with which. Well, camera, well, that uses visible light. Straightforward. One of the uses of light waves. This comes from when we learn about uses of electromagnetic waves. Television in the radio, spectrum, and TV remote is infrared. Something just to know. Learn the uses of them. Visible light and infrared are all part of the same electromagnetic spectrum, which all travels at the same speed. So therefore, simply, infrared travels at the same speed. Make sure you put a unit in there, that's important. But the only thing that differs is that from a very, very short wavelength, it moves to being a very big wavelength. So therefore, infrareds have a longer wavelength than visible light. Longer wavelength than visible light. Okay, so making good headway so far. And now here's one of those questions, as I describe them, sort of how science works. So you're given a situation that you need to then start interpreting some results. Now, let's, oh, sorry for the wobble there. Let's take a look at what we've got. 1 metre is 50 newtons. And that means that if I were to put 50 newtons on this spring, because in effect what we've got is a spring and different objets on the bottom of it. If I was to put something like 50 newtons, somewhere between there, we should get an extension of about 1 metre, so that's about right. Bearing in mind, of course, that the spring has a natural length and you're looking for the extension, so if that's the length of the spring without a weight, and that's the length of the spring with a weight, you're just looking for this, which is the extension. So So let's first of all work out the extensions, which are quite straightforward. Remember, you subtract this from the first value. So if I was to subtract, this would be 1 because it's 2 minus the original length. Lots of us get this wrong in the experiment in class by just minusing the individual values, but it should be the original length. So therefore, what would this be? 1.25, because if I minus that from that, I'd get that. This is 1.80. This would be 2.40. The extension here would be 1.60. I hope you see why this is and how I can do it quite easily. And so straightforward, I hope. Recall from what you've done in the experiments. Plot a graph of load against, well, I cheated a bit here. I'm actually going to show you one I did earlier. And it asks in the question, load on the y and extension on the x-axis. A little bit odd because our independent variable, which is the load, should often be on the x-axis, where it's reversed in this case. However, it has been nice because it has given you some values. So what you should be able to see was this is the load, the values are given, that's the extension. Now when you're doing a graph, these are the 5 points you ought to think about. One is the scale. This has been done for you, but the scale is important. Oops, there you go. Scale is important. Another one are the axes. Are they labelled? And with units, really important point. The points, are they correctly plotted? Is the line of best fit plotted? And the orientation of these the right way around, but this asked us to do it the wrong way around in effect. Nevertheless, here are the points. I've drawn a line of best fit. Some might have done something like this, going, oh, well, that's my line of best fit. But what you should really appreciate is that you know what this experiment is. You know that it's linear, and then it will start to bend as you hit the elastic limit. So therefore, try and work out what they're asking of you, and try and make it match what you've seen in class. So there is our line of best fit. Which extend it beyond its elastic limit? Well, I think the elastic limit looks around about here. So the last two are no longer behaving linearly. It's now not behaving linearly. So it's beyond the elastic limit. So I think we have the last two, the Van de Graaff. Careful with the spelling there. And Hippo skull. Right. What feature helps me, oops, there we go, to work out where the elastic limit is? It's when it stops being linear. So, where the line stops being linear. Yeah, I think that's a good enough reason for now. Okay, good. So, coming back, let me just exchange this piece of paper for this one here. Does the spring extend 1 meter for every 50 newtons as the specification quoted? Well, what I'm going to do is, in this area where it's still within its elastic limit, drawing that down a bit, is that the case? Well, look, if I have 1 meter extension, that's only required 40 newtons in order to do that. So I've said no, the spring extends 1 meter for every 40 newtons. And a good comment would be, because you've done this in class, you can say the gradient of that line, the gradient of the line is the change in the load divided by the extension, the rise over the run. The rise over the run, which gives us 40 newtons per meter, which does not equal 50 newtons per meter, as the specification said. Okay. Right, let's go to number 4. We've got Danny, sister Rebecca, and Dad Philip sitting in a boat. The engine switched off, and they're sitting and they're going up and down. So which is false? Water waves are transverse. Well, that's correct. Water waves longitudinal. Well, that's actually wrong. So straight away we know which one is wrong. because the other two make sense. The peaks will travel one wavelength in one time period, correct, and the successive distance between is the same as the yes, because the difference between peaks and troughs is the same. Okay, Danny says that it will push them towards the shore. Rebecca says no, just up and down. Philip says I'm not sure, perhaps they draw us out to sea. Who's right? Well, that is a tidal effect. That is often a wind effect. Rebecca is right because it's transverse waves, which means the vibration is up and down, and it's only the vibration that they're feeling. The energy goes in a direction, but you don't follow the energy, you're acting as if you're one of the things vibrating. So that is the reason why Rebecca is right. Good, okay, now let's think about what's happening here. You've got 1, 2, 3 peaks. 1, 2, 3 peaks pass him in 7 seconds. So that means we have 2 wavelengths. Time period, of course, is the time it takes for one wave to occur. So if we have 7 seconds divided by the 2 wavelengths, that gives us 3.5 seconds is the time period. What about the frequency? Well, the frequency, just you need to recall that equation is 1 over the time period, which gives us 1 over 3.5, which equals, if memory recalls, about 0.29, I think it is. I'm just going to double check to make sure it's right. Yeah, 0.29 hertz. So let's look at where the equation comes in. Equation, 1 mark. Substitution, another. Answer, unit, 4 marks. Excellent. Dog runs along and it keeps pace with the peak of the waves. In other words, it's going at the same speed of the wave. And it tells you there's a wavelength, and your previous answer gives you a frequency. So therefore, you can recall that velocity is frequency times wavelength, which is 0.29 multiplied by the 6, and that gives us 1.74 meters per second. 4 marks. Equation, substitution, answer, unit. Good, moving on. Sound, so it's another waves question. What's A? Simple, microphone. Let's just recall. Label the amplitude. Okay, that's just recall. Remember, it's the displacement from its resting point, not from peak to peak or peak to trough. It's displacement from the resting point. Increasing amplitude of sound will increase the volume. Okay, easy marks if you've revised. The graph shows the average results from a set of measurements. Interesting here, so amplitude, volume, depending on the distance you are away. And that makes sense. As you go further away, so the volume decreases or the amplitude decreases. It's asking here, of course, to find out at 2 centimeters what the average amplitude is. Well, just read off, and we need to be careful about reading it off. 1, 2, in divisions of 5, 17 centimeters. Don't rush those questions. They will only give plus or minus about 1 in any direction. What's the conclusion? Well, you just need to talk qualitatively about this. If you increase the distance, because you should always start by referencing your independent variable first, then what happens? The amplitude decreases. So referencing your experiment. Another easy one to pick up marks. Okay, number 6. Not so easy. A little bit, it just confuses people. It's a descriptive. It's not quite as straightforward. So let's look carefully at thermos flask. We have seen this in class before. And heat transfer is reduced in a number of ways by the vacuum conduction function. From silver surfaces stops the radiation, and the plastic cap stops conduction and convection. do we need to explain? Well, conduction because it's plastic, convection because it's stopping air from moving through this area. Okay. The vacuum between stops heat provided by conduction and convection. Why is that? Well, simply a vacuum means that there are no air particles. So, conduction and convection need air, stroke a medium to travel in. Hence, no heat transfer. Quite cunning. Okay, now looking a little bit more closely at the surfaces. What we have here is matte white, matte black, shiny silver, a heater, so it's receiving the same amount of infrared radiation, but the thermometers read very different things, 20, 29, 23. So, which one of these are more likely to have been read in each of these? We know that black matte surfaces absorb the most amount of radiation, so therefore it would make sense that that has probably caused the greatest temperature rise. So therefore, number 2. Why? Because black matte surfaces absorb most radiation. Hence, greatest temperature rise. Oops, there you go. Right. Which of these was not a control variable? In other words, which one did you not keep constant? Well, the distance between the heater and the metal plates was kept constant. The power of the heater, well, it was only one heater. The temperature before the heater was switched on, well, all 3 of them will have the same thing. So the colour of the metal plates, well, we varied that. So therefore, it's not a control variable. Good. What about the firefighter? Here there's a fire. How is the heat getting to him? Well, through radiation. If you want to try and remember this, you think to yourself, a fire heats you more through radiation than through conduction or convection. Therefore, why is the outside shiny? It's to reflect the radiation and keep cool. Okay, making great headway. Thermal energy transfers, we're not done yet. Here is question 7, talking about a hot plate heating a pan which heats the water inside. Particles in metal, how is heat transferred through the base of the saucepan? Well, of course, through conduction. However, we know there's a special case which metals conduct through free electrons. The C of free electrons, should we say, which is a metallic bond. So, yes, so how is heat transferred? Well, conduction, but the metals conduct through a sea of free electrons. The electrons transfer heat very efficiently. Good, what's next? Energy transfer of the water by convection currents. What happens here? Okay, so this is a standard what is a convection current type of question. So, first one, you heat the water at the bottom of the pan. Now, most people then say the particles expand. No, 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 no. So what happens is the space between particles expands, and that's due to them moving around more. That in turn makes them less dense, and so they rise. They cool, space decreases, they contract, more dense, sink. This, of course, is just the reverse, and that sets up a convection current. Okay, we've sort of carpet bombed that a little bit for only the 3 marks, but it's essentially just learn this by rote and then describe the application. So the convection current that's set up will heat the water. Good, something to learn. What is absolute zero? Well, I hope you all remember this, something to learn. Minus 273 degrees C, or 0 K. It's the temperature at which particles stop moving. Probably both marks needed there, description and a value. An iceberg has more random thermal energy than a metal ball at 300 degrees C. Might be surprising here, but why is that? Well, what we need to say is that internal energy is equal to the average energy per particle multiplied by the number of particles. Okay, the average energy per particle is in effect the temperature. So even though the metal ball has a much higher temperature, there are far fewer particles. So even though it's about 10 times, well, sorry, what's that? 10. If I multiply that, I'm going more negative. But even if that's 20, 40, 60, let's say 10 times greater, there are more than 10 times greater number of particles in the iceberg, and so therefore the iceberg has more energy. Really important to memorize that. Some things can have, and similar as an example, a cup of tea at 60 degrees, and let's say a bath of water at 60 degrees, though they have the same temperature, the bath has much more internal energy than the cup of tea. Right, electricity now. What is the X? Well, you should know it's a switch, but you're given 3 choices, and those two, that's just a let's hope nobody guessed either of those two. What's the total resistance? Well, in series, all you do is you add together the resistances, which gives you 24 ohms. The reading on the ammeter is 0.2. The current through the 6 ohm, it will be, this often catches people out. They think that things are eaten up as they go through here. Remember, the energy is used up, but not the number of coulombs per second. That's what this is reading, the number of coulombs per second. So therefore, the current in a series circuit is the same. It doesn't matter where you are here. Though it might not have much energy as it comes out, the current is always the same. Okay, charge. Calculate the charge. Right. Let's show a little bit of finesse here. It's not a right charge. Let's use the right word. Q is IT. Charge is current times time. Don't trip up with the idea of time. We have 0.25, and then we have 4 minutes, of which we want seconds, giving us, well, that cancels that, 60 coulombs. Okay. A circuit was set up in the diagram. For some reason, it hasn't printed. However, let's see what we can do without that. Define current. So this is the number of coulombs per second. You could get away with writing the rate of flow of charge. But I think that's more, the mathematician would say rate of flow. You're looking at something very tangible, the number of coulombs per second. Okay, current through the lamp. So what I think they're getting at, I'm sure they're probably talking about a parallel circuit this time. It is a guess. And they're saying probably through the lamp it's 0.2 and through the resistor it's 0.1 amps. So what's the reading on the ammeter here? 0.3 amps. You just add them together. Let's hope that's what the diagram ought to be. The resistance of the lamps is, well, if the lamp is allowing twice the current to go, that must mean the resistance here is less than the resistance of the resistor. So therefore, if the resistance of the lamp must be less than, smaller than, 60 ohms, because 60 ohms is allowing 0.1 to flow, so this must be less. Why? Well, you have a greater current, so less resistance. Okay, number 10, electrostatics. Once again, a point where we can get confused, so just bear with it. Let's see what happens. Okay, you have negatively charged plastic rod. And of course, this is moving, it's displacing, so there's definitely going to be a force of attraction between the two, that's why it's moving. So it should say here, the positive and the negative charge in the water are attracted. Well, you can't get both attracted. The positive and negative charge in the water are repelled. Well, you can't get both of them. The negative charge in the water is repelled, okay, by the rod, and the positive charge is attracted. Well, that would account for why that is. And finally, the negative charge in the water is attracted. Well, negative wouldn't be it, because we know that opposites attract. It's not that one. There's a really good YouTube clip on Veritasium, actually challenging the whole idea of this. Look it up if you're interested. Right, for B, bottle company mouthwash found a problem with automatic filling system because it starts going everywhere. Okay, so it says, explain why they become charged. Well, in all cases electrostatic, friction should be what you think about. But where is the friction? Well, plastic, bottles, and conveyor belt. What is an ion? Something that has lost or gained an electron. Remember, it's the loss or gain of electrons. You don't gain a proton. It's all about the electrons. You either lose it or you gain it. Why would earthing not be very useful here? Well, the reason why is because this is plastic. So even if you attach to earth something metal, it won't conduct away. So plastic does not conduct. So electrons stay put. Ooh, right. A bit of recall we needed here. Electrostatic precipitator. Well, hopefully you'll remember how this works. We have a grid here, which is negatively charged. And as the smoke comes through, it becomes charged. The edges of this, let's say a chimney, are positive, and so therefore the smoke is attracted to the edge, thereby reducing the soot from the emission that leaves the chimney. Harmlessly. So what would you need? You need a grid, negatively charged. You need a positive charged chimney. Then the soot is attracted to chimney. Therefore the gas leaving is clean. Good, good, good. Okay, back to a bit of maths. Right, so we need to, first of all, Andy and Damien running up the stairs, we need to calculate the weight. Okay, recall here, write down the equation, it's 4 marks, so you need all of these bits. You know that Andy's 80 kilograms times 10, giving you 800 newtons. 1, 2, 3, 4. It's okay to write 10 for G, that's good. Okay, next recall, work done. How much work is done? Work done is force times distance. The force is given in the previous question by the distance 2.5, which gives us a grand total of something like 1800. Brain stopped working. No, of course, 2000 joules. 1, 2, 3, 4. Takes 4 seconds to run up the stairs. Which one has more power? Okay, first of all, recall power is work done over time. What about, let's go for Damien first. Sounds like he's more powerful. Weight is mg, which is 80 plus 15. That sounds quite heavy really for Damien, but no problem. Times 10, which gives us 950 newtons. The work done is going to be 950 times the same height, which gives us 2,375 joules, and the power will be work done over time, 2375 over 5 seconds, 475 watts. It's powerful. Andy, on the other hand, is able to run up in, the power is going to be the work done over the time. It's got 2,000 joules and able to run up in 4 seconds, which sounds really unbelievable. But that gives 500 watts. So in actual fact, Andy is more powerful. There we go. Right, next one. Water slide. Simon and Ivor. What type of energy is Simon getting? Well, GPE, gravitational potential energy. Maybe write it out in full, to be not lazy. Do as I say, not as I do. What is the gravitational potential energy? Well, again, recall mgh, which is 80 by 10 by 8, giving us 6,400 joules. 1, 2, 3, 4. What does he have at the bottom of the slide? Well, we know that the transfer is GPE to kinetic energy if there's no friction in the system. We like having idealized systems. So therefore, the kinetic energy at the bottom will be the same as the gravitational energy at the top. So what's the velocity? Well, a half mv squared is your kinetic energy, which equals 6400. V is going to be 2 lots of the kinetic energy divided by half m square root. If we use the triangle, it's a bit tricky. Kinetic energy, half m v squared. V, kinetic energy divided by half m. Sorry, let me take out the 2. I was jumping ahead. Kinetic energy divided by half m, and then I square root it. So that gives me the square root of 6400 over 80 over 2. Square rooted gives me 12.6 meters per second. Superb, and that's it. Job done. Go back and check your answers. I hope you've all done well. Cool. Finished.